Chapter 2, Simulation Examples in a Spreadsheet or in Excel, Part 2. So let's see how we generate a random variable. As I said before, a random number is any number generated randomly between 0 and 1, right? And any method to generate a random number should have two properties. The first one is generating the random numbers between 0 and 1 with uniform distribution. And the second one, any random number generated at any time should be independent from the previous generated random numbers. Okay, so let's say we have a random number generator method and we can generate a random number like the function rand that we have in Excel, right? So now how we can generate a random variable. So a random variable, as we defined it before, is a quantity obtained randomly based on a specific statistical distribution. Okay, so here is the way that how we generate a random variable. At first, we need to obtain the CDF of the cumulative distribution function of that distribution. Okay, so for the specific distribution that we have, at first we obtain the CDF, cumulative distribution function, capital Fx. Okay, so and as you know, any CDF will be a curve like this. It should be increasing over the x. Okay, so now we know that the probability is always between 0 and 1, and the sum over all the probabilities should be add up to 1, right? So yeah, so by having this, the value of fx will be between 0 and 1, right? Now we generate a random number r, a random number, let's say using the rand function in Excel. Now, and then we set the random number to be equal to the fx, I mean to the CDF. Okay, so by having this equation, and then we can solve that equation for x, then we can obtain the xr, which we consider this as a random variable. So this is how we generate a random variable. At any time, we generate a random number r, and then we set that random number to be equal to the probability of that distribution, which is the fx, the CDF. Okay, and then by solving that equation for x, we can obtain the value of x, which will be a random variable. Okay, now let's have the process of generating random variables separately for continuous distributions and discrete distributions. So let's go first for continuous distributions. For continuous, the first step is finding the CDF function. Okay, so let's have an example here. Let's say our distribution is exponential distribution. So we want to generate a random variable from exponential distribution. As you know, the PDF, the probability density function, the PDF little fx for exponential is this, right? Now, the CDF of this distribution exponential would be this. Large fx, the CDF will be 1 minus e to the power of minus lambda x. And x is always greater than or equal to 0. Okay, so this is the CDF of the exponential distribution. The second step here is generating a random number. Okay, and as you know, we can do this in Excel by the rand function. So let's call the generated random number as r here. Okay, now the third step here is having the equation of fx, the CDF, be equal to the generated random number. And then we solve this equation for x, and then we can obtain x, which will be our random variable from exponential distribution as x. Okay, so let's solve this equation for x here. So we have 1 minus e to the power of minus lambda x equal to r, right? Then we will have 1 minus r equals e to the power of minus lambda x, right? Then we take ln function from the both sides of this equation. So ln 1 minus r minus lambda x. Now we can obtain the x as this minus ln 1 minus r over lambda, right? So now here r is the random number, right? So anytime in Excel we generate a random number, that will be r, and then we put that r in this equation, and x will be obtained based on that r. And here we call this as xr, which is our random variable from exponential distribution. Okay, so yeah, this is here, this is the equation for obtaining the random variable based on exponential distribution. Okay, so for discrete distributions, the first three steps are exactly the same. So for the discrete distributions, the first three steps are exactly the same, but the only difference is on the fourth step. So in step 4, in order to have this equation fx be equal to r, we find an interval in the fx of that discrete probability distributions that r lies between that interval. Then the upper limit of that interval xi would be our random variable here. Okay, so xi here would be the upper limit of that interval that r lies in that interval. Okay, so this is how we go for discrete distributions. Okay, let's have an example here for discrete distributions. Let's say our x values are these values: 15, 18, 21, 24, 27, and these are the probabilities of for each value. And here we obtain the CDF. As you know, for the CDF, we just calculate the cumulative probabilities for any x. So for 15, it's 0.24. For 18, we just add up to 0.24. We just add up these two values, 0.24 and plus 0.15. For 21, we need to add up all these three values, right? Which will be 0.39 plus 0.17. For 24, again, we need to add up all these four probabilities. And for 27, add up all these four probabilities. So this is how we obtain the CDF for discrete distribution. Now we have the CDF, and in order to generate a random variable, at first we need to generate a random number, right? Let's say we have generated the random number of as 0.65. So we need to find an interval in the CDF that this random number lies in that interval. So here, as you see here, we have these two numbers in CDF, 0.56 and 0.88. And 0.65 lies between these two values, so in this interval, right? And the upper limit here, which is 0.88, will mention the x, which is 24, right? So this is why we have x as 24 here. Or let's say we have another random number, which is 0.05, and it's between 0 and the first number, which is 0.24, right? And again, the upper limit here will mention the x, which is 15, right? So x will be 15 here, right? So this is how we go for discrete distributions. So let's have other examples for continuous distributions or other distributions. Let's have the uniform distribution here. For the uniform distribution, if it's discrete, then we can use this Excel function in Excel, just rand between min and max. So if it's discrete between two values, min and max, then we can use the rand between min and max in Excel in order to generate a random variable for this distribution, and that's it. But for the continuous, again, as you know, for the continuous, the fx, the PDF is this, right? 1 over b minus a, when x is between a and b, right? The CDF would be x minus a over b minus a, right? And if we set this CDF to be equal to the random number r and then solve this equation for x, x can be obtained. So x here would be a plus b minus a times r, right? Yeah, that's it. And this is how we have it here. So the xr, the random variable for uniform distribution, will be a plus b minus a times the generated random number r. Okay. And for normal distribution, again, we have a function in Excel, and it's so easy by using this function. It will be norm, which means normal distribution, dot inv, which comes from inverse. So yeah, it's inverse. And then we have three parameters in here: the rand, I mean the random number which we generate. So it's rand, it's the random number, the mean of the normal distribution, and the standard deviation of the normal distribution. Okay, and that's it. So yeah. Okay, we want to have an example here, which is a single server queuing model. So before that, let's have some definitions and assumptions for queuing model. So in any queuing model, we have these kind of events. The one is arrival process. So we have the event of arrival process, that customers arrive the system. So when a customer arrives the system, if there is no line and the server is idle, then that customer will directly join that server, and server will start serving that customer immediately. Okay, but if there is a line and some customers are in line, then this customer will join the line. Okay, so this is how we process for the arrival. And when a departure happens, I mean the event of departure happens, one customer completes the service and leaves the system, right? Then again, if there is a line, then the first customer in the line will join the server. Other than that, server becomes idle. So this is again how we process the departure event. Okay, so in queuing model, we may have different policies, different disciplines in order to process the events of arrival and departure. So let's see what are these different maybe policies. Okay. Yeah, the first policy is first in, first out. You know that FIFO, first customer comes in the system will be the first leaves the system. Last in, first out, or service in random order, or shortest processing time, or priority queue, what we see in emergency rooms in hospitals, for example. So these are different actually discipline that based on this discipline we have different logic for processing the arrival events. Okay, and for the queuing behavior, again we may consider different behaviors for customers. For example, a bulk behavior. in bulk behavior, customer leaves the system straight away if the line is too long. So in this discipline, not any customer will join the system. Customer arrives the system, and if the line is too long, then it gives up the system and leaves the system without having the service. So this is called bulk behavior. Reneging or renege. In this case, a customer joins the system even if the line is too long. It joins the system, but after a while waiting in line, and if the customer observes that the line is so slow, then the customer will leave the system without having the service. So this is called reneging. Or jokey behavior. In jokey behavior, customer will move from one line to another if they think they are in a slow line. So you see this kind of behavior in traffic jam in highways, for example, right? So yeah, these are again different behaviors of the customers in queuing model, and we may consider one of these discipline in simulating a queuing system. Okay. The queuing model, the queuing system, is one of the best examples for a discrete event simulation, DES model. So in discrete event simulation, as we talked before, the queuing system advances from one event to the next event. So here we have a feature event list, and each event has its own time of occurrence, and the process of the simulation approaches from one event to the next based on the time. Okay, so this approach is called advances of events. Okay, and we know that the discrete event simulation works based on this approach. But here, since we are going to implement this simulation model in Excel, so it's somehow impossible to implement this approach in Excel, or maybe it's too difficult. But here we are going to consider another approach, which is called tracking each customer explicitly. Okay, so here in chapter 2, in order to implement the DES simulation models in Excel, we apply the approach of tracking each customer explicitly instead of having the advancing of events. So in this chapter, we'll go by this approach, and then in chapter 3, we will go with the advancing of event list, and you will see the difference. You will see how these two approaches are different, and how, for example, Arena works and how a model in Excel works. Okay. So let's have our example here. This is a bank teller simulation model, or a single server model. So here we have just one server teller, and customers comes for taking the service from this teller, and we have a line here. Okay, so we have a teller, we have a line here, so customers join this line if there is a line in order to take the service. So these are actually the parameters that we have for our example. The inter-arrival time between customers 1 over lambda is 5 minutes. So here we assume that the inter-arrival time of for the arrival is based on exponential distribution. Okay, exponential distribution, and the mean for the exponential distribution is 1 over lambda, and here we have 1 over lambda, the mean inter-arrival time, as 5 minutes. So the inter-arrival time of for the customers is based on exponential distribution, and the mean of inter-arrival time is 5 minutes. Okay, 1 over lambda is 5 minutes. Okay, and we know that by having this equation, as we obtained before in Excel, we can obtain a random variable for the exponential distribution. Okay, and the teller service time is normal. So Here, the teller service time is based on the normal distribution with the parameters of mean. Mean here is 4, and sigma square, or the variance, is 3. Okay, so the mean of the service time for teller is 4 minutes, and the variance, or sigma square, is 3 minutes. Okay, and we know this equation, this function, actually this function in Excel, in order to generate a random variable based on the normal distribution. Okay, so this is our example, and we want to simulate this system, or this example in Excel. Okay, so let's before going to the Excel, let's visualize the operation of the system to see how it works, and then we'll go for simulating the system in Excel. Okay, so here we have generated the numbers for 5 customers. So by having the random variables for interarrival time and service time, we know that the first customer will be Adam, who arrives at time 2, right? So we start simulation by time 0. So from time 0 to time 2, there will be no customer in the system, because the first customer is supposed to arrive the system at time 2 based on the random variable that we generated by the exponential distribution. Okay, and Adam's service time is supposed to be 2.5 minutes, and the next customer, Bob, will arrive after 1 minute of arrival of Adam. Okay, so this means Bob will arrive the system at time 3, right? I mean, inter-arrival time between the first and the second customer is 1 minute. So Bob will arrive the system after 1 minute of arriving Adam. Okay, and yeah, and with the same manner, we'll go for the 5 customers. So here we have the inter-arrival time and also the service time of the 5 customers. So let's start visualizing the operation of the system. So as you see here, since the first customer, Adam, is supposed to come to service at time 2, so the teller is free from time 0 to time 2. Okay. At time 2, Adam arrives the system. So teller will be on serving the customer number 1, which is Adam. Okay. So teller will be busy on serving Adam from time 2 to time 4:30, right? 4.5, since the service time of Adam is 2.5, right? And the next customer, who is Adam, actually arrives the system at time here. As you see here, arrives the system at time 3. At time 3, right? And the next event here will be serving the Bob. So Bob will be in line from 3 to 4.5 until serving Adam is completed. Then Bob gets the service at 4.5, and its service time is supposed to be 4 minutes. So the teller will be busy on serving Bob up to 8.5, right? And the next customer, Chris, is supposed to come to service at time 12, because as you see here, the interval time between Bob and Chris is 9. So I mean, 9 minutes after arriving Bob, Chris will arrive the system. So Bob arrived the system at time 3. So after 9 minutes, will be at time 12. So Chris will arrive the system at time 12. So as you see here, from 8.5 up to 12, teller is again free, because there is no customer in the system for service. So teller will be free from 8.5 after completing serving Bob up to 12. Okay, and again at time 12, teller will serve Chris, and here as you see, the service time for Chris is just 1.5 minutes. So 12 to 13.5 will be the service time for Chris. Okay, and again from 13.5 up to up to 15, yeah, up to 15, Taylor will be free because Dan is supposed to arrive the system at time 15, 3 minutes after arriving Chris. Chris arrived at 12, so after 3 minutes will be 15. So the arrival time of Dan will be 15, and again Taylor starts serving Dan at 15, and its service time is supposed to be 4 minutes, so up to 19 Taylor will serve Dan, right? And the inter-arrival time between Dan and Eric is 10 minutes. So Dan arrived at 15, so 10 minutes inter-arrival time between Dan and Eric. So the arrival time of Eric will be 25, right? Yeah, the Eric will arrive to the system at time 25. So as you see here, from 19 up to 25, again the Taylor is free, right? So at 25, Eric arrives the system, and it's the service time for Eric is 3 minutes. So from 25 up to 28, Taylor will serve Eric. So as you see, this is how the system works. Customers arrive the system. If there is line, they join the line. If there is no line, they will go directly to the server, and server will serve customers. And if there is no customer line, server becomes free, and anytime that a customer arrives the system, again server will serve that customer. Okay, so this is how this single server queuing model works. So by understanding the operation of this system, let's go for simulating the system in Excel. So let's have the notations that we need to model the system as a simulation model. If the inter-arrival time of ith customer be AI, then the arrival time of nth customer will be this, sum over I of AI, okay? And if the service time of the ith customer be Si, so we generate AI and little ai and Si by the second distribution that we have, right? I mean by random number and then random variables. So by generating random variables based on the distribution that we have for inter-arrival time and service time, we obtain AI and Si, okay? So the wait time for ith customer Wi will be calculated based on this equation. I will show you how we obtain this equation after having the rest of the notations. The nth customer service start time, SSN, will be this. So we know that customer has arrived at time at this time, right? Let me show with a different color here, at this time, right? This is the arrival time of the nth customer. And if the customer waits in the line, then Wn will be the wait time. Then adding these two quantities will mention the service start time of customer N, right? And the departure time or the service end time for the nth customer, Dn, will be this. Yeah, the first term is the arrival time of the customer, Wn, the time that this customer waits in the line, and the Sn, the service time. So adding up all these three terms will mention the departure time or the service end time for customer N. Okay, and the sojourn time, the total time that customer N stays in the system, will be Wn plus Sn, right? And we have actually in total N customers in the system. So let's see how we obtain the waiting time. We can say the waiting time for customer, let's say N, will be the departure of the previous customer N minus 1 minus the arrival time of customer N, right? So yeah, customer N is supposed to arrive the system at An. So if the departure of the previous customer in the system be greater than an, then customer n needs to wait in line. But if the previous customer n minus 1 has departed the system before arriving the nth customer, then there will be no line, and customer n will join the system, will join the server immediately. So there will be no waiting time, right? So we can say the waiting time for customer n will be the departure time of the previous customer minus the arrival time of this customer, for let's say for customer n. Okay, so by having this equation here, we can say the dn is this sum over I going from 1 to n minus 1 ai plus wn minus 1 plus sn minus 1, right? Minus an, and for an again we have the sum over I going 1 to n of ai, right? So as you see here, in these two terms we have common terms. From I going from 1 to n minus 1 are common, so they will cancel each other. Then at the end we will have this wn will be wn minus 1 plus sn minus 1 and minus an, right? So this is why we have this equation here. And since the dn minus 1 can be actually sooner than an, so this can be a negative number, right? So when in case of negative, so there is no waiting time. So this is why we have the maximum between 0 and this quantity here. Okay, so this is how we obtain the waiting time for each customer. Okay, so this is the flow chart of our simulation model. In general, at the start we have initialization, and then we generate random variables, update statistical counter, and then is simulation over? No, we go back to generating random variable and update the statistical counter. If not, we actually report the results, and that's it. So in details, in the first step, we set the customers, and we are going to simulate the system for n customers. So here we generate the parameters or data for n customers, and then we set I to be 1. So we start from the first customer. Since we are going to track customers by one, I mean we will track each customer, and then we'll go for the next customer. So this is why here we have the algorithm based on the customer. So I equals 1 means the first customer. So we have the a0 as 0, and we have this is our initialization. So we generate the interval time for the ith customer here. Since I is 1, so we are generating the interval time for the first customer. And then we compute the arrival time based on this formula. Okay, and then we compute the waiting time for the ith customer, wi, based on the equation that we had in previous slide. And then we compute the service time of I mean the start of service for customer I, which will be arrival plus the wi. Okay, or alternatively it could be maximum between ai and d I minus 1. I mean the arrival time of ith customer and the departure of the previous customer. Okay, and then we generate the service time for ith customer si, again based on the random variable, and then we find the ith customer departure time di, which will be ssi plus si, and we can obtain the sojourn time, and the server idle time will be ssi minus di minus 1. I mean if the start of service for customer I is going to be greater than the departure time of the previous customer, then in this case a server will be idle. Other than that, there will be no free time. Okay, and we terminate the simulation when I becomes n, and that's it. Okay, so this is how the simulation algorithm works for this system. And at the end, we can calculate some measures as the performance of the system For example, the probability of customers to wait can be calculated by this formula: number of customers wait divided by the total number of customers n. Or average inter-arrival time, we can take just the average between the inter-arrival times: average service time, average waiting time, average sojourn time, and average waiting time of those who wait, right? We sum over the waiting times divided by the number of customers who wait. And for the server, we can say that we can calculate the server idle time here. We can add up these quantities, and then it will actually determine the total idle or total free time of the server. And for the server utilization rate, we can obtain it by this formula. So yeah, after any simulation, after all the runs, we can calculate the performance measures like this for that system. So we need to define the specified measures for each Unix system. So usually for the single server model, in general, we can define the performance measures like this. Okay, so you will see how we implement this simulation model in Excel in the next part. Okay, thank you.